So in this video, we'll be talking about setting up a graphical function synthesis problem, and also talking about Chebyshev spacing, which is a way of saying, where do I want to place my precision positions to give me the best solution? In other words, one that minimizes the error between what I ideally want to have with my function and what I actually achieve with the synthesized solution. So first of all, let's talk a little bit more about function generation and what it is, why I'd use it. Again, this is coordinating the rotation of an input link with the rotation of an output link, or the translation of one of those. And so, some classic examples will be adding a driving dyad to an existing 4-bar mechanism as a way of applying an input to it, and then controlling through the range of motion where do I want it to be relative to the crankshaft that's setting up the timing for the mechanism. Something like a washing machine agitator mechanism is a classic example of a function generator, where we have an input that's providing rotation, and we're creating rotational output that's oscillating the drum back and forth and creating the agitation for the close. Another very classic example is a mathematical function generator. So this is before digital computers. We had analog computers, and you would often have these analog function generators, which are really a little computer, and we'll talk about how to synthesize that. So our focus here will be on a mathematical function generator and really just setting up the problem, and then in the next video lecture we'll synthesize a solution. So what would this problem look like? Well, imagine that I want to create a function generator that is going to create the function y is equal to x to the 0.8 power. And I'm going to do this for x being from 1 up to 3, and you can see what the y as a function of x looks like on the plot right there. So we want to create a mathematical function generator, or a linkage, that creates this function. So how do we start? Well, that's what we're going to look at right now. So how we start is, first of all, saying, where should I place my precision positions? And we want to minimize what we call the structural error, which is basically what's the total error of the linkage that I create relative to the function that I want it to emulate. And what we're going to do to place these precision positions is use what we call Chebyshev spacing. So Chebyshev spacing is just kind of a fancy name for where should I place the precision positions. And in this case, I'm looking at a 3 precision position problem, kind of the first step. We'll look at 4 and 5 positions later on. But for a 3 precision position problem, I'm going to look at it this way. So first of all, for Chebyshev spacing, I take this range that I'm going to be operating through from 1 to 3, x being 1 to 3, and then I draw a circle of the diameter delta x, so the diameter here would be 3 minus 1, or 2, and I draw that circle on the x grid that I've set up there. Next thing I'm going to do is, based on the number of precision positions that I have, in this case I have 3, I'm going to then draw a regular polygon with 2 n sides. So n, again, is the number of precision positions. In this case, I would have a hexagon being 3 times 2, 6 sides. So I then inscribe this regular polygon within this circle. And what this polygon then does is it tells me where should I be placing my precision positions. And so you'll notice that with this regular polygon that I inscribed, I always have the sides of it being vertical. And so in the case where I had 4 precision positions and I put in an octagon, I would still have vertical sides here and then come up and then have a horizontal top. But I always make sure I have vertical sides here. Why? Well, what this is telling us is that if we look at where every one of these vertexes are of our regular polygon, and we drop a line down, in other words, I have a vertex right here and I bring that line down, this is going to be my first precision position. I then go to the next vertex and I bring that down, so 2 will be my second precision position, and then right over here for our third. So that is the general approach, or what Chebyshev spacing tells us as to where we should place our precision positions to minimize the total structural error of our problem. So what do we need to do to finish this off? Well, we go to just a little bit of trigonometry and say, all right, for this case I've got 30 degrees right here. For this hexagon, and from that then I can calculate, all right, if I have this unit length here, what would be these positions, and I get 2.866, I believe, and then on the other side I get just over 1.134. So those would then be my precision positions. So instead of picking the 2 extremes and saying I'm going to have 1 being precision position 1, 2, and then 3 as a third precision position, you notice that I bring those edge precision positions inward slightly, and that will minimize the total structural error of the solution that I create. So that tells us where we should stick our precision positions. Now we need to further develop this to actually get to the point that we have enough information to do our synthesis. So this is what we've already talked about, what our function is that we're going to create and the Chebyshev spacing that we used. So now let me create this table here. And what this table is going to do is help me figure out how do I take these x positions, turn them into y positions, and then one more step, go to what angle should I actually be synthesizing for my mechanism. So I've got the precision positions as well as kind of a start value here and an end value. So that gives us the full range that we're trying to get through, but these are the 3 precision positions. And I plug those into my equation and I can calculate what my y value would be for those 3 precision positions. Now, I also need to figure out what angles am I going to be moving through, and so I need to define a little bit more here. And I'm going to say that I have an input range of 60 degrees, so this is the beta angle or the range that the input link rotates through, and the output link I'll say rotates through 90 degrees. So as 60 degrees will take me all the way from 1 to 3, and 90 degrees will take me all the way from whatever the y value be, 1, all the way up to what it would be at x of equal to 3. And now I need to just map these values. So I'm going from 0 to 60 and 0 to 90. So I'm going to map these values, these beta angles, and I'm going to say, what's the total range of beta? So in this case, it's 60 degrees, divided by the total range of x, which is 2 in this case. And then I provide this mapping, x of j. So in the case of I'm at 1.13 minus x of 1, or 1. I then just run those numbers, and I can figure out, all right, in the first precision position, I'm at 4 degrees for my input link, and then 30 degrees, and then 56 degrees. I use this same mapping then for the output link. So these psi angles now, where I want to have a range of 90 degrees total, I then use this same mapping to take my y values into psi angles, and as I apply those, I get 7 degrees, 47 degrees, and 85 degrees. So this then sets up enough information that we can move into the next step, which is actually doing the synthesis of our problem. And so these values that I've highlighted in red here, these will be what we're using in the next graphical synthesis video to actually synthesize the 4-bar mechanism that provides this function, this mathematical function that we want to generate.